Okay, let's dive right into this explainer. We're going to be exploring the absolutely fascinating intersection of a once-in-a-generation mathematical breakthrough and, well, the very physical limits of computer hardware. We hear a ton about AI and the theoretical magic of software. But today we're grounding that magic. We're looking at what actually happens when the absolute perfection of mathematical law crashes directly into the uncompromising, friction-filled reality of a silicon microchip.
So here is our roadmap for today. 1. The Math Rosetta Stone. 2. Bridging Math and Matter. 3. The Thermodynamic Toll. 4. Shape versus Payload. And finally, 5. Wiring the Seismograph.
All right, let's kick things off with Section 1, the Math Rosetta Stone.
To really understand this, we need to rewind to a 1967 proposal that honestly makes everything else we're discussing today possible. It's called the Langlands program. Proposed by Robert Langlands, this is often referred to as the grand unified theory of mathematics. Think of it kind of like a universal translator for math. It proposed that seemingly impossible, mind-bending problems could actually be solved by translating them between two entirely different mathematical universes. Basically, if you get stuck in one universe, you translate the problem, solve it over in the other universe, and then just translate the answer back. Pretty elegant, right?
And this brilliantly connects two totally distinct domains. On one side, you have the discrete, strictly logical world of prime numbers and algebraic equations. We'll call that the number side. And on the other, the wave side, you've got the continuous spatial world of geometric surfaces and analytic waves. It is completely wild to think about, but for decades, mathematicians strongly suspected these two sides perfectly mirrored each other. The catch? Proving that this translation was completely lossless, meaning no information gets corrupted when you move from those discrete numbers over to the continuous waves, well, that was an incredibly daunting task.
But that actually changed recently. In 2024, mathematician Dennis Geitzcorey and his team published a colossal 1,000-page proof resolving what's called the Geometric Langlands conjecture. This monumental achievement earned him the 2025 Breakthrough Prize in Mathematics. What it essentially proves is that this translation between the two universes really is flawlessly lossless. Now, the source material jokes that this is a discovery that less than 15 people in the world can actually understand. But hey, the core takeaway for us is profound. The absolute mathematical bridge between discrete logic and continuous geometry is real, and it is perfectly exact.
Moving on to Section 2, Bridging Math and Matter. So the obvious question here is, how in the world do we bring this abstract mathematical perfection into the applied physical universe of computation? How exactly do you take a 1,000-page proof and apply it to an AI that's running on a physical microchip? Well, this brings us to a core operational mantra for AI and hardware. Bits replace, matter displaces. In a purely logical AI space, semantic bits are basically weightless, right? You can swap out words and drift meaning with literally zero friction. But when you ask a physical computer to execute that logic, the heavy physical matter, the electrons and cache states in the silicon, they can't occupy the same space at the same time. The matter has to actively physically move to make room. So we can actually map the math directly to engineering by comparing the semantic state of AI logic with the hardware state of physical silicon execution. The semantic state, the bits, is a lot like the number side of the Langlands program we just talked about. It's logical, abstract, weightless. The hardware state, the matter, is like the wave side. It is physical, it's spatial, and it's topological. Think about it like this. You're basically taking the weightless ghost of an AI's intent and forcing it to possess a physical silicon body.
Which naturally leads us to Section 3, the Thermodynamic Toll.
Now, in pure math, that bridge we were just talking about is completely free. But in physics, the universe absolutely charges a tax. Nature just doesn't allow for infinite precision, and that introduces a massive collision between mathematical theory and physical reality. That brings us to this incredibly specific exact number right here, 0.003. That represents the KE, the 0.003 bits of coherence that are surrendered every single time information crosses the boundary into physical silicon. And here's the kicker. You literally cannot engineer this down to zero. It is the inescapable toll of the physical universe acting on information.
This all comes down to Landauer's principle. This is the law stating that erasing or changing information physically releases heat. Because of that, thermodynamics charges a toll for every state change, and that causes this lawless semantic drift. Because that 0.003-bit tax is constantly being paid, the AI's semantic intent slightly degrades the second it hits the hardware. And this degradation? It accumulates into what we call quantifiable trust debt. This is actually the core problem engineers are facing right now. Semantic drift isn't necessarily a bug or a failure of the software. It's the measurable distance from mathematical equivalence. It's literally the insurable drag resulting from the physical friction of computation.
Imagine for a second particles suspended in fluid, kind of bumping around randomly in what we call Brownian motion. While individual AI semantic trajectories wander randomly due to that physical friction we just discussed, the diffusion constant, which is the thermodynamic tax rate itself, remains an exact substrate-independent invariant. Meaning, the individual physical runs are always going to drift and get a bit messy, but the mathematical law governing exactly how they drift, that is perfect and exact. The trajectories drift, but the law holds.
All right, let's jump to section 4, shape versus payload.
So here's the million-dollar question. How do you actually measure something that is constantly degrading? Well, we have to strictly separate the actual semantic meaning of the AI payload from the exact topological shape of the physical hardware cache displacement. This is a huge paradigm shift. The payload, the data content, the meaning itself, pays the thermodynamic tax. It loses coherence, it gets bruised along the way. But the shape of the displacement, that geometric footprint of the hardware completely rearranging itself to accommodate the new semantic weight, that remains mathematically exact.
Because these two factors are completely independent of each other, it's amazing to think that our hardware acts exactly like a seismograph. Think about it. A seismograph doesn't understand the quote-unquote meaning of an earthquake. It doesn't care if a building falls or a mountain shifts, it only measures the shape of the z-axis displacement. By locking abstract bits strictly to the displacing matter, the hardware acts as our seismograph, giving engineers what they call multiplicative information gain. You independently verify the semantic meaning on one side and the physical shape on the other. If they both agree, boom! The proof is mathematically ironclad, even if the payload lost a tiny bit of fidelity along the way.
Now, in Langlands math, this specific mechanism is called a Hecke eigensheaf. If that sounds super intimidating, don't worry. Just think of poking a water balloon with your finger. The local spot you poke stretches and distorts, right? But the overall amount of water and the global shape of the balloon adapts perfectly without popping. This is exactly how our silicon mold works. The AI semantic edit forces displaced electrons to leave a verifiable footprint. The local data twists and degrades to pay the thermodynamic toll, but the global geometric shape of the cache eviction remains mathematically pristine.
Bringing us to our final part, Section 5, wiring the seismograph.
So, how do we actually prove this fractal identity map architecture in the real, messy world of computer engineering? I mean, it's one thing to understand the math, but how do you actually wire the seismograph to measure this friction? The timeline here is honestly staggering. Mathematicians just proved the abstract bridge in early 2024. Just a year later, the applied silicon mechanism was patented in April 2025. And by May 2025, engineers generated the very first real sparse grid hardware receipt. That means they successfully measured an independent semantic witness and an independent physical hardware witness agreeing on the exact same coordinate. For the first time, the math and the matter finally shook hands.
To pull this off, engineers are working through a ridiculously strict checklist to eliminate what they call hollow circles. They're replacing stale baseline measurements with a live, 11 million times a second hardware walk. And they aren't just doing this in theory, folks. They are running millions of live physical tests per second to map out the exact true physical friction zone of a semantic edit into a live thermodynamic heat map. Once that sensor is fully calibrated, they scale it up to tens of thousands of receipts to mathematically prove the invariance of the physical shape. The sheer scale of this engineering feat is absolutely incredible.
By proving that the semantic logic of an AI actually has a measurable, bidirectional link to the physical state of the hardware, it leaves us with this final staggering question to ponder. Are we building the physical laws of motion for information? We aren't just creating clever software algorithms anymore. We're engineering a thermodynamic bridge that perfectly prices the physical reality of abstract thought. And that, well, that completely changes how we measure, verify, and ultimately trust the systems that are going to run our future. Thanks for joining me for this explainer. I'll see you next time.